Norman, I think I got you. Check. Okay, so my plan was to just finish 5.2. I think I'll be able to do that comfortably today. So I might sneak in some of 5.3. I don't have to. We've got plenty of time, actually. I mean, after 5.2, there's only 3 sections for just about 2 weeks. So if I really wanted to push it, I could probably finish everything by next Friday the 4th, but I'm not really going to try to do that. Okay, quiz tomorrow, I'll give you the Riemann sum stuff. So just like before, I'll give you a graph, and you might do the left sums, the right sums, and the midpoint root. Okay, and that'll be it. And everybody knows Thursday and Friday, no school. Okay, enjoy your Thanksgiving off. So school tomorrow, but no school on Thursday, no school on Friday. Quiz isn't due until Monday at 12:10 as usual. Anyway, okay. All right, so we very well may finish early today. And then I'll let you ask questions, and if there aren't any questions, we can stop. Or maybe I'll sneak in some of 5.3, but I don't have to since we're okay time-wise. All right. Okay, so here we go. I got up to about 11, so let's do 33, 34 problems at the end. Okay, now 33 and 34, you can actually find the values of these definite integrals because we don't have to approximate. Here, they're all straight lines, so we know how to find actual areas of squares, rectangles, triangles, and so forth. Okay. 34, the only curved part is this, but they tell me that it's a semicircle, part of a circle. So I can also find the exact value. Okay. So these, you're not chopping it up into so many pieces. You can find the exact value. Okay. So let's look at 33. Evaluate each integral by interpreting in terms of areas. Okay. So we know for an integral, anything that's above the x-axis is counted as positive. Anything below the x-axis is counted as negative. Okay, integral from 0 to 2 of f of x dx. They're asking for the exact value now, not an approximation, exact value. So the area under the curve, well, in this case, the curve so-called, is just a straight line. Okay, so I'm tracing out the region in my question. So from 0 to 2, you're going up there, along the diagonal, straight down and back. One more time, up, diagonal, down, and back. And the way they have it, you can just pretty much count squares. So I got 1, 2, 3, and 2 halves make 4. So the answer to A is simply 4. Okay, so again, the area under the graph, I got 1 square, 2 squares, 3 squares, and these 2 halves make up 4. So the answer to A is 4. Okay, now how about integral from 0 to 5? Okay, so follow the logic. Okay, we already said this was 4, right? 1, 2, 3, 4. From 2 to 3, there's 3 more. 1, 2, 3, so that's a total of 7. Right? So one more time. That's 4. Up, across, down, back. That's 1, 2, 3, and 2 halves. That's 4. 5, 6, 7. And then what about this? That's a triangle. So it's 1/2 base times height. 1/2 of 2 by 3 is 3. So that's a grand total of 10 now. Okay, so the answer to B is 10. 1, 2, 3. These 2 halves is 4. 5, 6, 7. And we argued that this was 3. Or another way you can think of it is this whole region here, this rectangle is 6, right? 2 by 3. Watch this. 1, 2, 3, 4, 5, 6. Okay, that cuts it in half. That's 3. So I have 4 here, 5, 6, 7, plus 3 is 10. So the answer to part B is 10. Now, integral from 5 to 7. Here's 5, here's 7. That's going to be negative because it's below the x-axis. So let me find the area of this triangle and just count it as a negative. So that's 1/2 2 by 3. Right? That's 2, that's 3. 1/2 of 2 times 3 is 3. So the answer to C is negative 3. Okay, so negative 3. And finally, D, from 0 to 9, all the way across here. Now, we said we had 10 positive from 0 to 5 already. Okay, one more time. 1, 2, 3. These two halves make 4. Between 2 and 3, 5, 6, 7. And this triangle makes 10. Okay, so from 0 to 5, it's 10. Now, we argued that this here was 3 negative. So 10 minus 3 is 7. 1, 2, 3, 4. And a half. That's negative 5. So between 7 and 9, that's 1, 2, 3, 4. And this makes another 1 whole. So 5 more negatives. So 7 minus 5 is 2. So the answer to D is 2. Okay, so again, we said this was 10 positive, minus 3, 7, minus another 5. So 33D grand total should be 2. Okay. 34. Integral from 0 to 2. 0 to 2. I got this triangle. Positive. So 1/2 base times height. 1/2 of 2 times 4 is 4. So the answer to A is 4. B, integral from 2 to 6. Negative. Semicircle. What's the area of a circle? Pi r squared. What's the radius? Radius is 2. I got a semicircle. So it's 1/2 of pi r squared. Pi times 2 squared is 4 pi. Half of that is 2 pi. So this area is 2 pi. The integral is negative 2 pi. Okay, so the answer to B is negative 2 pi. So one more time, follow the argument. Okay, sorry, I don't have any more hands. I needed a finger to draw this, and I need a finger to hold up the book and everything. But, okay, what's the area of this semicircle? The radius is 2. Formula for the area of a circle, pi r squared. Okay, I got 1/2. So it's 1/2 pi r squared. R is 2. So it's 1/2 of pi times 4, or 2 pi. The area is 2 pi, therefore the integral is negative 2 pi. And finally, C, integral from 0 to 7. What's that piece right there? 1/2, positive. So from 0 to 7, I got this, which was a positive 4, right? That's 4. Negative 2 pi and a half. Positive, positive. 4 plus a half, 4.5 or 4.5 minus 2 pi. So the answer to 34C is 4.5 minus 2 pi. Sorry, I can't write it down. I don't have enough hands to show you everything. Okay, if we were meeting face to face, I would project the book and write something on the board. Well, I can't write on the board because I don't have a board. Okay, so the answer to C is 4.5. That's 4, positive. That's a half, positive. So that's 4.5 minus 2 pi. Okay. All right, that's as much as I can show you for that. Okay, then the problems at the end, 35 to 41. I think I already alluded to 41. 41. Integral from 1 to 1. no matter what the function is, square root of 1 plus x to the fourth, who cares? How much area is there if I go from 1 and I end up at 1? You didn't go anywhere, so the answer is 0. 41 is automatically 0. Okay, 35, 37, and 39, then we're done. Evaluate by interpreting in terms of areas. So what we have to do is draw the picture and then gauge something from the picture. So 35, integral from -1 to 2 of 1 minus x. Let me show you that. -1 to 2 of 1 minus x. What's the shape of 1 minus x? Straight line. Slope of -1, y-intercept of 1. Okay. Or you can just do a quickie graph. -1 and 2. So I plug in -1. 1 minus -1 is 2. Plug in 0, you get 1. Plug in 1, you get 0. Plug in 2, you get -1. So this is the graph. Okay, so the area bounded by the graph and the x-axis, anything above is counted as positive. Anything below is counted as a negative. Let me try to hold it up. If I raise it up, then it's a little bit easier to focus. Okay, so this area I call it A1. This area I call it A2. Now, area is always a positive quantity, right? Not the integral, but the area. So an integral, you can think of it as a signed area, S-I-G-N-E-D. Okay, so what is this area? It's 2 by 2. So 1/2 base times height. 1/2 of 2 times 2 is 2. Area 2, A2, that's 1/2. 1/2 of 1 by 1. So for the integral, my abbreviation for integral is I. Integral is +2 minus 1/2 because this is below the x-axis. So the final answer is 1.5. Okay, so I just draw the picture so I can see what's going on, and I interpret in terms of area. So this is 2 units, this 1/2 unit. Okay, since we're doing an integral, anything above the x-axis is counted as positive. Anything below the x-axis is counted as negative. Okay, so +2, -1/2 comes out to be 1.5 or 1.5. Okay. Okay, 37, I wasn't going to do the whole thing, but I'll just set you up for it. Integral from -1 to 0 of, -3 to 0. Here we go. 1 plus radical 9 minus x squared dx. Okay. And we want the exact value. First, let's just look at this. The 1 doesn't bother me. I know what's going to happen to the 1. Let me consider this. And what happens to this? Move the whole graph 1 unit up. So what's the graph of this? Okay, so I took a little time out. Let me call that y. Y equals square root of 9 minus x squared. Square both sides. Y squared equals 9 minus x squared. Add x squared. X squared plus y squared equals 9. Aha, I recognize that. It's a circle, center of the origin, radius of 3. But in the original problem, it was y equals blah, blah, blah. That means y can only be positive, so I don't have any negative stuff. And they tell me we're integrating from -3 to 0 in the original problem. Okay, so I don't want any negative y's. Okay. And I'm only going from -3 to 0. So this is the region in question. So quadrant 2, y equals square root of 9 minus x squared. Now I will go back and incorporate the +1. That just moves the graph up 1 unit. Okay, so this is the point -3, 0. This is 0, 3. By the way, what happens when you plug in -3, right? -3 squared, 9. 9 minus 9 is 0. Square root of 0 is 0. Plug in 0. 9 minus 0 is 9. Square root of 9 is 3. Plus 1 means move the graph up 1. So this becomes -3 comma 1. 0, 3 becomes 0, 4. So there we go. -3, 1, double check. Put -3 here. -3 squared is 9. 9 minus 9 is 0. Square root of 0 is 0. Plus 1 is 1. 0 gives me 4. Plug in 0. 9 minus 0, 9. Square root of 9 is 3. 1 plus 3 is 4. Okay, so your task is to figure out the area of this rectangle. That's easy. And you got 1/4 of a circle. So that should be very easy. And it's all positive. Right? So this is 1/4 of pi r squared. I'm practically giving away the answer. Right? And you can figure out the length times height of that rectangle. Okay. Okay, then 39, and I'm practically done, folks. I have so much time left, I can probably sneak in a little bit of the next section, but not too much. So we'll probably finish early, unless you have questions. Okay, 39, integral from -4 to 3 of absolute value of half x dx. Okay. So the best way to figure this out is to draw a quick graph for 39. Let's pretend we don't know the answer. Integral from -4 to 3. So I just made a little table. From -4 to 3, right? -4, -3, -2, -1, 0, 1, 2, 3. Plug in -4. Half of -4 is -2, whose absolute value is 2. And keep going. Plug in -3. Half of -3 is -1.5, whose absolute value is 1.5. -2. Half of -2 is -1, whose absolute value is 1, and so on. And just keep going. Follow the table. They said to go from -4 to 3. 0 gives me 0. Half of 0 is 0. Absolute value of 0 is 0. And maybe just, you can do this as well as I can. Just plug everything in. Plug in 3. 1/2 of 3, 1.5. Absolute value 1.5, 1.5. Okay, so this is what you get. -4, 2. 0, 0, 3, 1.5. So that's the shape. I know it's going to be positive. It's all above the x-axis. So I just figure out area 1 and area 2. Both will be considered positive. So this triangle, 1/2 base times height, 1/2 of 4 by 2. Again, these are distances. Distances are always positive, so you don't plug in -4, right? Yeah, this x-coordinate is -4, but as a distance, this is 4, right? And as a height, that's 2. So 1/2 of 4 times 2, 4. Same thing here, 1/2 base times height. So this is 3 units. That's 1.5. So 1/2 of 3 times 1.5. I guess there should be another parenthesis here. Anyway, 2.25. So the integral from -4 to 3 is 4 positive plus 2.25 positive, net result 6.25. So there we go. Okay. All right, folks, I'm actually done with section 5.2. So I'll sneak in a little bit of 5.3, not that much. Then I'll stop and let you ask questions. And then if you have none, we can just stop. Okay, so tomorrow I'll do more 5.3 and quiz on Riemann sums. So I will give you a graph and you estimate using left endpoints, right endpoints, and midpoints. Okay, and then I should mark these off. And then I'll give you the quiz, and then we're off for Thanksgiving holidays. Okay. All right, so I'll sneak in a little bit of 5.3. The topic is the fundamental theorem of calculus. Okay. Big rule. There's actually two parts to the fundamental theorem of calculus. There's fundamental theorem of calculus part 1, fundamental theorem of calculus part 2. Now, you don't feel like writing fundamental theorem of calculus. I don't feel like writing fundamental theorem of calculus all the time. Mr. Stewart, the author, who's Mr. Stewart? The guy who wrote the book. He doesn't always feel like putting fundamental theorem of calculus either. Okay, so I will abbreviate with FTC, fundamental theorem of calculus, FTC. There's two parts, so I'll call it FTC1, FTC2. So be that as it may. Okay, so some introduction. Here's a new weird function. It's kind of like an area function. G of x is the integral from a to x of f of t dt. Okay, x is a variable, a is a constant. Okay, so a might be 5, -21, pi, whatever. X moves. Okay, so here's the picture. We're talking about a true area under the curve now. So here's A. Imagine fixing A, but you move X. Okay, so can you imagine, if I can just take my pen. Okay, so X moves. If I move it this way, and I move it this way, I get a different amount of area, right? The area depends on what the X is. If X lines up with A, then the area is 0, right? But for this one, it looks like if I keep going further and further to the right, I get more area. If I go to the left, I get less area, right? So g of x is the integral from a to x of f of t dt. So x moves. It's a strange area function. The lower limit, a, is fixed, okay? But x keeps moving. Okay? X moves around. So figure 2, they draw this weird picture. I'm trying to give you a feel of this g of x integral from a to x f of t dt. Okay, so they have this. So g of 1 means, okay, in this case, g of x is defined as the integral from 0 to x of f of t dt. So 0 is fixed, but you keep moving x around. So g of 0 means integral from 0 to 0. We know that's 0, right? The 0 on the bottom is fixed. Now we move the x on top. G of 1 means the integral from 0 to 1. So that's going to be 1 unit, right? 1/2 base times height. Okay, so they got the picture over here. G of 1 is 1. G of 2 is the integral from 0 to 2. That means they're going from there to there. That's 3. 1 square, 2 squares, and 1/2 base times height, that's another 1. So grand total of 3. G of 3 is this picture. See what's happening? You're moving the x, as it were. So g of x is defined as the integral from 0 to x. So you're fixing the 0, but you're moving x back and forth, and it's kind of like you're getting an area function. Okay. So they say g of 3 is 4.3. Now you have to just estimate. Okay, so they say we have 3 here. They're guesstimating that that's about 1.3 units, that curved part. Now they're saying g of 4 is approximately 3 because you get some negative region here. So this positive region minus this negative region. Okay. And g of 5, notice you're always starting at 0. And now you're moving out to here, so you're getting more negative stuff. They're estimating that that's about 1.7. Okay. So that's sort of what's happening over here now. Okay, so you have this strange area function, so to speak. Okay. Okay, and just to show you where Mr. Stewart says FTC1, yeah, there it is, FTC1, Fundamental Theorem of Calculus, Part 1. There's also going to be Fundamental Theorem of Calculus, Part 2, FTC2. Okay. Here is FTC1. I'll talk about it shortly. Page 394. If you want to put this on your cheat sheet, you may. Okay. I will go over a mini proof of it. Okay. If f is continuous on a closed interval from a to b, then g of x integral from a to x, so constant here, variable here, f of t dt, x between a and b. It's a continuous function and differentiable on a and b, and g prime of x is f of x. Okay. Main thing is the derivative of this integral is the function itself. That's sort of what they're saying. Okay. If you want to shorten it and just leave this part out, continuous and differentiable, okay, g of x is this weird function, integral from a to x. What you want to recognize is this is a constant, this is a variable. Yeah, you could say f of x dx, but you're not supposed to say x here if I already put x here. So they switch to a different letter, t. So don't get scared by f of t dt. You're not supposed to write x if that x is there. Say they pick a different letter, f of t dt. The derivative of this function is f of x. That's what they're trying to say. Okay. They go over a proof. I'll go over my own mini proof of that also. Okay, so this is FTC Part 1, Fundamental Theorem of Calculus Part 1, and I'll show you my version of it now. And maybe that's all I'll do today. So Fundamental Theorem of Calculus, this is actually Part 1. So maybe I should sneak in a 1 here. Oops, if I can get in a 1. FTC 1. Okay, f is a continuous function, so here's f. Okay, here's a, here's x. So g of x, integral from a to x of f of t dt. I will trace out g of x. Here, here, down, and back. It's this white space here. One more time. Integral from a to x of f of t dt is this, down, and back. Okay, I'm going to add a certain value, h. This is a tiny little h. So g of x plus h, area under the curve from a to x plus h. That's this. Up, out to here, down, and back. One more time. Up, over here, down, and back. So do you agree if I subtract g of x plus h minus g of x, I just get this shaded region, right? Because g of x plus h is everything out to here. G of x stops right here. So if I subtract the two, I just have this red region. It's approximately a rectangle, base times height, for a continuous function. Okay. So I put f of x star. So what's x star? X star is just some number between x and x plus h. Okay. It could be the left endpoint. It could be the right endpoint. It could be the midpoint. Technically, it can be any point between x and x plus h. It doesn't matter because h is going to approach 0 in just a circle. Okay. So the red area is approximately base times height. Okay. It's an approximate rectangle. Divide both sides by h. Looks like this. G of x plus h minus g of x divided by h is approximately f of x star. X star is any number between x and x plus h, including x and x plus h. Then we take the limit as h approaches 0. Okay, so let h approach 0. These two get really, really tight in. If x and x plus h get real close together, for continuous functions, this looks more and more and more like a real rectangle. So we take limit h approaches 0, g of x plus h minus g of x all over h. Limit h approaches 0, f of x star. Okay, and here's a key thing. Okay. If h approaches 0, it doesn't matter if I pick the left endpoint, the right endpoint, the midpoint, or anything in between. Okay. These two are going to converge to just x. They'll get closer and closer to x. So the right-hand side is just f of x. The left-hand side, that's the very definition of g prime of x, right? That's a definition, the limit definition of a derivative. G prime of x is f of x. So getting back to over here, g prime of x is f of x. So that's fundamental theorem of calculus part 1. FTC part 1. Okay. So what do you need to know about this? You're not responsible for this derivation. So you might say, I have no idea what you did over here. Okay, that's okay. I was supposed to show you. You don't have to duplicate that. What you do need to know is this theorem. Okay, that if this is a definition of g of x defined as an integral, constant on the bottom, variable on the top, then g prime of x is f of x. So I'll write that over here now. Given a continuous function f, g of x is defined to be integral from a to x. You must have constant here, variable here. Like 5 here, x here. So what happens if it isn't that way? Then I'll show you. Then g prime of x is equal to f of x. It sounds like a real weird theorem, but we need it to prove FTC2, fundamental theorem of calculus part 2, which is actually the more important theorem of the two. But FTC2, fundamental theorem of calculus 2, is based on fundamental theorem of calculus 1. Right, that's why I have to show you fundamental theorem of calculus part 1. Okay, so this kind of goes along with what Mr. Stewart has. And then I'm just about done. Okay, so the rest of the time I'll let you ask questions, and if there aren't any, we're finished, and I'll continue more with section 3 tomorrow. Okay, so f is continuous. G is defined as the integral from a to x. It's sort of like this area function. It's sort of like what we were doing over here. A is on the left side. It's fixed. X keeps moving, right? So if I keep moving x, I get a different area, right? I keep going left and right and so on. So it's this weird area function. Put this on your cheat sheet. G of x is the integral from a to x of f of t dt. Must be constant here, must be variable here. So what if it isn't? Then I'll tell you. Okay. Then g prime of x is equal to f of x. The derivative of this function, what do? All you do is just put that x right in there. Just substitute right here. That's what I'm saying over there. Okay. So g prime of x is equal to f of x. Then I can finally start showing you how to do some of the homework problems in 5.3. But even if I don't get to that, we're good. We got plenty of time for that. So maybe tomorrow I can start sneaking in a little bit of 5.3, but not that much, because I want to give you enough time to do the quiz also. Good. All right, folks, I think I'm done. Let me check the chat if I can get it the right way. I believe I can not lose the shared screen. Yeah, and get the chat. So let me check the chat. Let's see. Let's see, for number 37, 3 plus, put in the back of the book. Well, I have to see what we're talking about. $37. Oh yeah, the one that I worked on. Okay, so the answer to 37, in other words. All right, so we have this region right here, right? So that's a quarter circle plus this. So this is 3 times 1, which is 3. So it's 3 plus whatever this is, 1/4 of pi r squared. The radius is 3, right? So pi times 3 squared, 9 pi. That's a quarter of it, so 1/4 of 9 pi, 9 pi over 4. And there's a plus 3. So that's where it came from. That's fine. So it looks like the answer should be 3 plus 9/4 pi. That one. All right. Okay, how do I know to add 3? I got this rectangle right here. Okay, so this is my quarter circle. That's the 9/4 pi. This is 1/3. So the total area under the curve is 9/4 pi, I guess, plus 3 over here. All right, folks, anybody with a question? Otherwise, I'm done. Okay, we'll call it a day. All right, so tomorrow I'll do a little bit of stuff and give you the quiz, and then we'll have a nice Thanksgiving. Okay? All right, have a good day, everybody.